Hi, welcome to this presentation on error detection and correction. So I'd like to start off by describing where error detection and correction occurs in biology, and then lead you up to a hands-on paper exercise where you actually go through the logic of error detection and correction, and then show you how that logic's turned into a circuit and implemented on a modern field programmable gate array. When you get sick, how does your body know what's a bad cell and what's a good cell? How does it know which cells to kill? How does your immune system work? If we chemically synthesize DNA, we end up with about 1 out of every 100 with some kind of a problem in it, in the DNA. The ribosomes in our body get this error rate down to 1 part in 10,000 by error checking the transport DNA. This is a ribosome. And the DNA synthesis process our body uses gets the error rate down to 1 part in 10 to the 8th, or what is that, 10 million? 1 out of every 10 million is bad. And that supports evolution. And it supports evolution where it doesn't cycle, it doesn't bounce back and forth, it actually progresses. Our bodies are amazing machines. Our computers are even better. In fact, they prevent evolution of computers right now. There's a lot of other things that are preventing evolution, but being too good at finding errors and correcting them is a feature of our modern computers. But let's listen to this MIT professor doing the keynote presentation at ShmooCon, which is a hacker convention.
It's not that we're copying biology, but you can think about it as forward engineering, not reverse engineering biology. By doing sort of good engineering, we're figuring out why biology does what it does. So this is the ribosome. It's my favorite machine. It's the protein that makes proteins. Messenger RNA comes in. The mRNA has all the properties of a good modern code. tRNAs bring in the amino acids. The amino acids are exactly like molecular Lego. And then the ribosome iteratively assembles them. And so if you look at the numbers, chemical synthesis has an error rate of about 1 part in 100. The ribosome makes an error rate of about 1 part in 10 to the 4 because you can error check the tRNAs. And then DNA synthesis is more sensitive, so it expends a thermodynamic cost to do an extra step of error correction. And DNA copying has an error rate of 10 to the 8. And that's this exponential scaling. The exponential scaling that gives you exponential complexity, which in this case is U, comes from the ribosome isn't just a code describing a thing. The code is the thing. The code becomes the thing. It's coding discrete construction of error-coded materials. And it's not a new idea. I didn't think of that. It's a 4 billion-year-old idea. That's the evolutionary age of the ribosome, and it's the most conserved part of biology. But we're coming to appreciate that's the real deep meaning of digital fabrication. Again, it's not a computer controlling a machine. It's actually putting the codes into the materials. What's new now is we're ready to start building things that work like ribosomes, but in material systems that don't exist in biology, like high electron mobility electronics.
So what causes all these errors? There's lots of causes of them, but the most uncontrollable, the one that we can never get rid of, are these cosmic rays. They're basically high velocity parts of atoms that hit our atmosphere and split up into all these dangerous particles that end up giving us cancer, corrupting our cells. In a computer, they mess up the hard drives, they mess up our wireless communication, they mess up our RAM. So what happened in the 1950s when computers were rooms filled with vacuum tubes is they couldn't figure out which vacuum tube was bad. They couldn't figure out and replace them fast enough. So they had to begin building this error detection and correction mechanism. And a fellow named Hamming published a paper in 1950 that seeded this whole process. You might have noticed when you buy a hard drive, you'll buy a 1 terabyte hard drive, but you only get 900 gigabytes. That's because the other 100 gigabytes is being saved for error correction codes. You look when you buy RAM, there's different kinds of RAM. It varies in price based upon how much error correcting code is built into the hardware itself. Wireless communication could not happen with our cell phones if we did not have error correcting built into the digital transmission of our telephone calls. So we're going to watch 2 videos now that just show you how fragile a computer is, how easy it is for a cosmic ray to mess up first RAM, dynamic RAM, and then a hard drive.
You are working on your computer, start a new document, and save it on your hard drive. You start typing away, and about 20 minutes later, the power to your computer is disconnected. Perhaps a power failure or somebody tripped over your power cord. Your screen goes black, and you have to power up your computer again. When you open the document you are working on, it contains none of your work from the last 20 minutes. Gone. Let's learn what happened and why it's important to understand how your computer's main memory works. The main memory of most computers consists of dynamic random access memory, or DRAM. It is considered a type of random access memory, or RAM, which means that information stored on it can be accessed in a random order. This makes it a really fast type of storage and therefore ideal for use as the main memory for a computer system. In contrast, information stored on a hard disk drive needs to be read in a particular order, which makes it much slower. Information in DRAM is stored using an integrated circuit which contains transistors and capacitors. A single pair of 1 transistor and 1 capacitor stores 1 bit of information. The capacitor can hold a low charge, also called discharged, or a high charge, also called charged, which correspond to 0 and 1 respectively. The transistor acts as a switch to read the state of the capacitor or to change its state. Capacitors slowly leak their charge, and therefore the capacitor charge needs to be refreshed regularly by restoring the charge. That is the reason this type of RAM is called dynamic.
So dynamic RAM is like a paper cup with a hole in it. And when it's filled up, it represents a 1. When it's empty, it represents a 0. It leaks so fast that if there's water in there, you've got to top it off 10,000 times a second. And if you miss just one of those, because a cosmic ray hits, because it's going bad, because something else glitched, then all of that memory starts to go bad. Let's look at hard drives.
A home computer is a powerful tool, but it must store data reliably to work well. Otherwise, it's kind of pointless, isn't it? Let's look inside and see how it stores data. Look at that. It's marvelous. It's an ordinary hard drive, but its details, of course, are extraordinary. Now, I'm sure you know the essence of a hard drive. We store data on it in binary form, 1s and 0s. Now, this arm supports a head, which is an electromagnet that scans over the disk and either writes data by changing the magnetization of specific sections on the platter, or it just reads the data by measuring the magnetic polarization. Now, in principle, pretty simple, but in practice, a lot of hardcore engineering. At its simplest, it's a piece of ferromagnetic material wrapped with wire. As it passes over the magnetized sections of the platter, it measures changes in the direction of the magnetic poles. We call Faraday's law. A change in magnetization produces a voltage in a nearby coil. So as the head passes a section where the polarity has changed, it records a voltage spike. The spikes, both negative and positive, represent a 1, and when there is no voltage spike, corresponds to a 0. The head gets astonishingly close to the disk surface, 100 nanometers in older drives, but today under 10 nanometers in the newest ones. As the head gets closer to the disk, its magnetic field covers less area, allowing for more sectors of information to be packed onto the disk's surface. The key element of the platter is the magnetic layer, which is cobalt with perhaps platinum and nickel mixed in. Now, this mixture of metals has high coercivity, which means that it will maintain that magnetization and thus data until it's exposed to another powerful magnetic field. One last thing that I find enormously clever, using a bit of math to squeeze up to 40% more information on the disk. Consider this sequence of magnetic poles on the disk surface, 0, 1, 0, 1, 1, 1. A scan by the head would reveal these distinct voltage spikes, both positive or negative for the ones. We would be easily able to distinguish it from, say, this similar sequence. If we compare them, they clearly differ. Engineers, though, always work to get more and more data onto a hard drive. One way to do this is to shrink the magnetic domains, but look what happens to the voltage spikes when we do this. For each sequence, the spikes of the ones now overlap and superimpose, giving fuzzy signals. In fact, the two sequences now look very similar. Using a technique called partial response maximum likelihood, engineers have developed sophisticated codes that can take a murky signal like this, generate the possible sequences that could make it up, and then choose the most probable.
Every time engineers pack more data onto a hard drive, they increase the likelihood that it's going to get mixed up with other data, that it's going to get corrupted, that it's weaker, and the electronics has to be more sensitive. This makes it more susceptible to cosmic rays. This means that the error correcting codes have to be increased, and this delicate balance continues to increase the capacity of hard drives. There will be a limit, though. We're rapidly approaching it. They're thinking about trying to stack the magnetic fields instead of vertically at an angle and overlap them like shingles on a roof. It's amazing what's going on, but it only works because of error correcting codes. The most primitive kinds of error correcting occur in normal everyday speech. I say something to you, I look at you, you nod your heads, or you say, hey, can you say that again? So you either acknowledge what I said and let me go on, or you say, knack, please, negative acknowledgement, please repeat what you've just said. A more complicated version of error correcting is to send the exact same data 3 times. And you assume that one error event will occur and corrupt maybe one of the 3. So you pick the 2 that match and say that's what the original transmission was. So that's a form of error correction. None of this stuff is ever perfect. What you do is you get it better and better and better. And the fellow who started this was Richard Hamming, who didn't die all that long ago. We're going to explore it by looking at these 3 circles and doing some even odd comparisons within the circles. Being passed around are pieces of paper that look like this. We're going to start here on the left-hand side. This is the input, so squares represent the input. We're going to go through a sending or storing circuit, so it's going to send it through the airwaves, stored on a hard drive or stored in RAM. And then we're going to build a receiving circuit right here that looks at both the data and the extra stuff that was saved on the hard drive or transmitted through the air. And what we're going to do is we're going to change one of these from a 1 to a 0 or 0 to a 1. And you can pick whichever one of these you want to change. So you basically copy almost all of these and change one of the bits. And then we're going to show you over here how the receiving circuitry detects which bit you changed and corrects it. So I'm going to switch to the document camera now and physically do this, and you're going to follow me. Okay, so hopefully you've successfully filled out this sheet of paper and you corrupted a bit right here and detected that it was corrupted and fixed it over here. What we want to do now is turn this into a circuit. And we start that process by naming the steps we went through right here. So what we did is we created parity. P stands for parity. And we have 3 parity creators. We have 3 circles here. So that sending circuit's pretty simple. The receiving circuit's a little bit more complicated. What we do is we have these parities coming in that were sent through the air or stored on a hard drive or temporarily stored in RAM. And what we're doing is recomputing them. So this P1 is recomputed from these data bits. And then this P1 is compared with that P1. The same thing's true for P2. This P2 is compared to that P2. This P3 is compared to that P3. And if they match, they're good. If they don't match, they're bad. If P1 and P2 are bad, then what we did is we toggled D1. So what we did is we recomputed the parity. We recomputed P1. Then we compared, and then we looked at all the circles values, the 3 circles right here, and if 2 or 3 of them were bad, we figured out which bit needed to be fixed. So the last step right here is to fix the bit. So there's 3 sub-circuits inside this receive circuit. Here we can see the words being translated into circuit symbols. This is an exclusive OR gate. It's basically an odd detector. And by creating an odd detector, then the whole circuit is always even. So here we again see the XOR gate being recomputed with the same chip over here in the receive circuit. And here we see the original P1 and the recomputed P1 being compared to see if that P1 is good or bad. Right now the bright green indicates that they're all good, and none of these bits need to be changed. But if any of these outputs right here go to a bright green, then that indicates that D4 needs to be toggled. If it's a 0 coming in, it needs to be a 1. If it's a 1 coming in, it needs to be a 0. So this is the actual circuit. And so what I'm going to do next is switch to the actual circuit simulator and pound on these, and we can watch the 1s and 0s fly around. Show you how we built these circuits physically with wires and chips in 2008. This is pretty much the last time we built the circuits using this technology. This is called hole-through technology. I'm going to put it in fast motion so it goes through pretty quickly. Okay, so the more modern way we create circuits is we send commands down a USB cable attached right here. And then that USB cable goes into the field programmable gate array. These are 2 pictures of field programmable gate arrays. And what they are wires and blocks. So this is a logic block. It's a bunch of NAND gates. With a NAND gate, you can create any kind of part in a computer that you want. It's a primitive building block of everything. And then these wires right in here where these intersections are, you can burn holes in them temporarily. So when you send commands in here, you're basically traveling down to one of these intersections and routing data in and out of these blocks. In from a pin, into a block, around another block, and then out to a pin. Software, or something that looks like software, is what's used to create the instructions that go in the USB cable and tell this chip how to wire itself. These are the commands that replicate this circuit. For example, here to create these parity detectors, to compute P1 for the circles, what we need to do is XOR 3 wires coming into them, and then send the output here to S1. So instead of calling it D1, I'm calling it S1. Here we see the commands for comparing the recomputed parity with the received parity. So this represents this 2-input XOR gate right here. That's what these commands represent. And then here what we're doing is computing the corrected bits. This is the AND gate. It's a 3-input AND gate. So you can see this and this and this. So there's 3 inputs, and various ones of them are knotted. These little circles right here represent knots. And then finally out here you can see the fixing commands. These are so basically what we're doing is just naming wires. All these things right here are not array names like in a programming language. They're just names of a bundle of wires. Wire 0, wire 1, wire 2, wire 3, and we're calling that bundle of wires CB. That's all there is to it. Modern programming of chips. So what you're going to see now is this video being played, and it's the actual commands that have been sent into the field programmable gate array, and we've hooked up some LEDs, 4 LEDs to those field programmable gate arrays as output, and we have these 4 switches as the original input, these 4 as the possibly corrupted received bits, and then these LEDs right here represent the good if they're on parity circles or bad if they're off parity circles.
Okay, well this is a demo of the Hamming 7-4 circuit. You can see I've got the switch up, these 2 down, that one up. These first 4 switches represent what's initially transmitted. Then these 4 switches represent the exact same thing, which is received. Now right now the first 4 and the second 4 match. So the lights right here, you can see this light right there is on, off, off, on. Those represent what's been fixed, or the corrected bits. These 3 lights represent circles, the parity circles, and right now they're matching. All 3 are on because these first 4 bits and these second 4 bits match. Okay, this first switch turns off. If I make it bad, all 3 parity circles go out. You see the lights flashing. That means right now it's bad. It's still being corrected because these 2 lights are on. So that's the bit that's common to all 3 parity circles. Now the second bit, just 2 of the lights go out. So they're hidden by my thumb. But the parity, 2 of the parity circles are bad, but the bit's still being corrected because you can see the 2 rightmost lights are on. Okay, so now we get 2 of the parity circles being bad. That's good. 2 of the parity circles being bad, but the bit's still being corrected. And then finally we get to the last one. You can see 2 of the parity circles are bad, but still being corrected. There it is, good. There it is, bad.
So to summarize, the error correcting code evolution inside of a computer hasn't followed the evolution of biology. In the space of, well, since 1950, we've gone from Richard Hamming's elementary foray into this to very sophisticated codes that involve mathematicians being employed to create them, The most modern ones are called Turbo and LDPC. The most current ones that are being implemented right now are RSV. The Voyager probe uses Goulet. And this is pretty interesting. It takes 18 hours for bits to travel from Earth to the Voyager spacecraft. And if the Voyager spacecraft can't correct them and has to send back a negative acknowledgement, that's another 18 hours. So we're talking a day and a half to make a round trip to the Voyager spacecraft. And if there's lots of corruption of the data in the travel to the spacecraft, no data is ever going to get transmitted. So this is the only reason the Voyager spacecraft works today is because there's error correction codes being added to the data being sent to it. The Turbo and LDPC codes are so much better than biology. It makes you wonder what the future is going to have in store for us when we start making the other parts of a computer that mimic how biology evolves. Listen to that ShmooCom keynote address. It's an hour long. It'll just change your perspective of the world. Thanks for coming.